Well, hello and welcome to the 32nd lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. We were in the middle of finding out uh, finding out expressions for these quantities which are called the invariants of this system. Dk is the dimension of Bk. Okay. What we did for that was we wrote down this matrix W0. So, for us W is u y or yu. What did I write? I think u y. Yes, u y. Okay. If W is u y, then W0, W1, W2 dot 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 Wk, a typical k size W kth restriction of the trajectory W is going to look like the following. I am going to put here my independent variables x0, u0, u1, u2 dot 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 uk. Okay. So, x0 multiplies to this column, u0 multiplies to this column, u1 multiplies to this column, u2 multiplies to this column, then I have dot dot dot, and finally I have the uk. W0 is u0 y0, right. So, first will be 0 identity 0 0 dot 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 0. Second will be, both of these correspond to W0. Okay. This is y0 and y0 is going to be c times x0 and d times u0 0 0 dot 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 0. What is W1? That is going to be u1 first so 0 0 identity 0 dot 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 0. Then this is going to be C A, this is going to be C B, this is going to be D 0 dot 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 0. I hope I have not made a mistake here. This is corresponding to W1. Let me just quickly check whether that is what this was. C A C B D 0, right. C A C B D 0. Now I am to find out W2. For W2, the first entry is U2, which of course is this identity dot 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 0. Then this is going to be CA squared, CAB, CB, and then D dot 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 0. That is my W2. This trend will continue, and Wk will be C a to the power k, C a to the power k minus 1 b, C a to the power k minus 2 b, C a to the power k minus 1 b dot dot dot. It will go up to d, but I have actually skipped one row in my zeal to complete this matrix. I forgot, so I have to get this guy up below a little bit, 2 below it is, right. This should be okay. I need to have 0 0 0 0 dot 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 identity also here, right, because Wk's first row is Uk. Now I am going to get rid of these guys, this is understandable, and these brackets also I need to make a little longer. I am going to get rid of these guys as well. I am not giving this matrix a name, or maybe we can call it M. This matrix Mk, right. Claim is that Dk is equal to rank of Mk. It is an easy claim, easy to prove claim. Why? Because dk is dimension of bk. This is a free vector, I can choose it to be anything. So, this vector is of what size? This vector is size are there are n such state variables plus k plus 1 into m, that is the size. So, this is a free vector, these inputs can be anything, these vectors, and x 0 also the initial condition can also be anything. So, therefore, the dimension of this, so therefore, bk is in fact equal to image of this matrix mk, or the column span of this matrix mk, col span, whatever you wish to call it, image or column span of this matrix, right. So, therefore, that means dimension of bk must be equal to rank of this matrix mk, that is it. So, therefore, dk is equal to rank of mk. So, I need to find out the rank of this matrix. How do I find out the rank of this matrix? To get the rank of this matrix, you see, I can do row operations as well to find out the rank, because row rank is the same as the column rank. No, if I do the row operation on this guy, of course, the column span will change, right. Row operation keeps the row span intact, it does not keep the column span intact. The column span will change. So, I am not claiming that when I am doing row operations the image will also remain the same, that is not the idea anyway. But I can, because I am interested only in the numbers, because I am interested only in finding out the rank of this matrix, I can do those do those row operations even when the column span will change. So, now if I do row operations, see, by doing row operations I can make this guy, this guy, this guy, this guy disappear, this guy, this guy, this guy also disappear, this guy, all of them I can make them, I can make this guy also disappear. All of these, you know, empty guys will be just zeros. Yeah, all of these guys will be zeros. And so, there are these identities sitting there. How many such identities? Each identity is size m, is not it? Because it is size m, and there are how many of them? There are, you can check, there are k plus 1 of them. So, these identities I can club together, you know, after row operations. So, let me just write this down, then it will become clearer. After row operations, notice when I do these row operations, none of these row operations do anything to this first guy, to this first column, yeah, because for each of these row operations this corresponding entry in the first column is 0, 0. So, nothing happens to this first column. So, therefore, after row operations and after doing a little permutation of the rows, all I am going to get is 0 identity 0 dot 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 0, 0 0 identity 0, and this trend will continue. I think this trend will continue 0 0 0 identity. Yeah, I have such a matrix m m m, and what is the size? There are q plus 1. So, why did I write q? There are k plus 1 such blocks. Oops, I am too messy today. Blocks, yeah, and then here I have c a dot 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 up to c a to the power k, that is the matrix, and this is a big 0. So, now look at this guy. What is the rank of this guy? The row rank. The row rank of this guy, of course, is k plus 1 times m. These are identities. No, this is full row rank. And then I have this guy. So, the rank of this matrix mk is then equal to k plus 1 times m plus rank of this matrix c a squared dot 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 up to c a to the power k. Does it not look familiar? This is the observability matrix, isn't it? Yeah, this is the observability matrix. What is its rank in general? How do I find out this, the rank of this? This is not the full observability matrix though. You see the rank is going, so this is a part of the possibly a part of the observability matrix, but it can be bigger than that also, bigger than the observability matrix also. Yeah, when you stop at k exactly equal to n minus 1, that is when you get your observability matrix, but this is the general form of a part of the observability matrix, or this is like a how do you call it, this is like so this is of the form of the observability matrix, right. What is its rank? We know that for observability, when k is equal to n minus 1, it should be full rank. Yeah, okay, it should be full column rank, it should be full column rank when k is equal to n minus 1 for observability, and we have assumed observability though. But here we are not interested in that observability question per se, we are interested in finding out the rank of this matrix. How do you get this rank? To understand this rank, there are various ways to do that, but there is this very fascinating way of representing the rank of this matrix, and that is going to be important for us. Let us see that. Okay. So, so let us say we assume observability, right. Okay. Now, look at r to the power n first. Notice that r to the power n can be written as r to the power n. Okay. I look at kernel of C. Let me give some names also. Yeah, this matrix I call OK, observability matrix. OK is defined as C A dot 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 up to C A to the power k. Yeah. Okay. So that way O0 is just C. Now notice, if I look at kernel of O0, null space of O0, then kernel of O0 is a subspace of Rn. Yeah, and what we have seen before, if you quotient Rn by kernel of O0, quotienting my subspace, then this direct sum with kernel of O0 is a direct sum decomposition of Rn. Yeah, but now look at kernel of O0. Kernel of O0 contains as a subspace kernel of O1. Do you agree? What is kernel of O1? O1 is C A. Anything that is in the kernel of this guy automatically is in the kernel of C. So, therefore, kernel of O1 is contained in kernel of O0. So, then kernel of O0 can further be written as kernel of O0 quotiented by kernel of O1 direct sum kernel of O1, which means I can refine my earlier direct sum decomposition by kernel of O0 was this. This was kernel of O0, which can further be written as kernel of O0 quotiented by kernel of O1 direct sum kernel of O1. But now kernel of O1 contains kernel of O2 as a subspace. So, no wonder that I can write Rn as Rn quotiented by kernel of O0 direct sum kernel of O0 quotiented by kernel of O1 direct sum kernel of O1 by kernel of O2 direct sum kernel of O2, but kernel of O2 by kernel of O1 O3 direct sum kernel of O3 by kernel of O4, and this continues forever. Do I have to go all the way forever? Well, actually you do not have to, because after some time these kernels will turn out to be, after some time you will not get anything new. Okay. After some time, if it is observable, then once you go to O n minus 1, its kernel will turn out to be 0, okay. And from then onwards, if you go anything O n plus 1, O n plus 2, all of those kernels will be 0. Yeah, because you already have a full column rank matrix, and you know, as you keep on adding more and more new rows, it does not matter, it still remains full column rank. Okay. But what we will do is we will give these guys some names. We will call this guy M0, we will call this guy as M1, this as M2, this is M3, and so on. And then under observability we notice the following. Suppose I look at this Rn, and then I look at I do the following. I look at Rn kernel O0 direct sum dot 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 kernel direct sum kernel O say k minus 1 quotiented by kernel OK plus all of these I can club together and write kernel of OK. Yeah, is that all right? Now this is M0, right? This is M0, and this up to this one, this will be MK. This guy, however, what is this? So now suppose, so these are the dimensions. Yeah, these are the dimensions. Dimension equal to M0, dimension equal to M1, dimension equal to M2, and so on. So let me write it down here explicitly, that I am defining dimension of kernel of O k minus 1 by kernel of O k. I am defining this to be equal to MK, right. Now when you know that when you have a direct sum decomposition, the dimension of these guys add up and give the dimension of the ambient space. What is the dimension of this guy, however? Dimension of this guy is, by rank nullity theorem, n minus rank of OK. All right. Now what do I have then? So from here I have n is equal to M0 plus M1 plus dot 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 up to MK plus n minus rank of OK. Yeah. So these are dimensions of these components, and then finally this component has dimension equal to n minus rank of OK. Then n cancels out from here, and all we have left with is the fact that rank of OK is equal to, lo behold, M0 plus M1 plus dot 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 up to MK. Lovely, isn't it? So now we go back. We go back where? We go back to our this guy. Is this so? This guy. Dimension of Bk is equal to rank of Mk, and that is equal to k plus 1 into M plus rank of OK. So let me go back then. Now dimension of Bk, okay, dk by definition is the dimension of Bk, that is equal to rank of Mk, and that is equal to k plus 1 times M. Yeah, I have been writing M though, but without explaining it so far. I am sorry, I said that all these are size M. I am sure you have understood what that means. Let me write it somewhere so that it is not. Input U is size M every time. Okay, okay, k plus 1 times m plus rank of OK, but that is equal to k plus 1 times m plus m0 plus m1 plus dot 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 up to mk. Lovely, isn't it? That is the dimension of dk. Okay. Now, so what is rho k then? Rho k is equal to dk minus dk minus 1, which is equal to k plus 1 times m plus m0 up to mk minus now k times m plus m0 plus dot 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 up to mk minus 1. So, when you subtract, what are you left with? We are left with rho k must then be equal to m plus mk, because all of those guys would have cancelled out. Great, no? Yeah. And you know, one can also understand that why is rho k a non increasing sequence, because each time it is m plus mk, and these mk numbers are non increasing. What is this mk? mk is the rank of, you know, this dimension. Look at this. This is mk. mk by definition is dimension of kernel of OK minus 1 divided by kernel of, I mean quotiented by kernel of OK. And once again, by this law of quotients, it turns out that this is equal to dimension of kernel of OK minus 1 minus dimension of kernel of OK. This difference is mk. Yeah. So, when you go to this bigger OK, so I have this OK minus 1, and then I add something, namely C a to the power k here, yeah, and now the dimension of the kernel of this big, yeah, which is smaller, you know, which is smaller than the dimension of kernel of this, that difference from this dimension. Okay, so the rank is increasing, so the kernel dimension is decreasing. So this kernel, this number is bigger than this one, so that is why mk is a non negative number. And once again, following the same logic, that if there is something, okay, see, if some rows are, if you look at the ranks, no, rank of these guys, if some rows are linearly dependent up to this point, they will continue to have same dependency patterns here also when you add these new rows, because you know from linear algebra it follows that if there is, so suppose I have C a dot 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 up to C a to the power k minus 1, yeah, and suppose I take a linear combination of these guys, alpha 0 plus alpha 1 plus dot 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 up to alpha k minus 1, and this linear combination goes to 0. If this linear combination goes to 0, notice that this also implies if you take now alpha, multiply this by a from the right. So, you have alpha C a plus alpha 1 C a squared plus dot 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 up to alpha k minus 1 C a to the power k, that will also continue to be 0, isn't it? But these are now rows from this bigger matrix. Yeah, you see, these are rows from the bigger matrix. So, therefore, like before, this shift invariance property, like before, when you have this thing, you know, each time as far as this difference in the dimension is concerned, the decrease in the dimension of the kernel at the kth stage will be more than the decrease in the k plus first stage. That is why these numbers mk's will decrease. Think about this. This is a food for thought. Think about this. Think about why. Think about why. Just plain rank nullity theorem, nothing else. Think about why M0, M1, M2 and so on. Once you understand that, it will be even clearer why row k's are decreasing. Okay. Now, interestingly, what we notice here is the following. Yes, is the following. What is rho infinity? Yeah, look at this thing. Look at this thing. What is m infinity? First, tell me what is infinity? M infinity. M infinity has to be 0, right? Because when you are doing this, after k becomes more than or equal to n minus 1, yeah, these numbers will become equal. No, all the dimensions are equal. We have seen all the kernels are equal. We have seen. So these quotients are just 0. So therefore, mk will become 0. That means m infinity is 0. If m infinity is 0, rho infinity is m plus m infinity. So this will be equal to m. So you see, rho infinity has a meaning. Rho infinity is in fact the input cardinality of the system. Remember that input cardinality thing that we discussed long back. This is the input cardinality of from the time series also you can find out the data about its input cardinality. That is rho infinity. Moreover, if you now look at this sum m0, m1 plus m2 plus dot dot dot, you see this actually goes to 0. You see these numbers m0, they converge to 0. So therefore, this in fact is a finite sum, although it looks like an infinite sum, it is a finite sum, because beyond a point all of them are 0. Because it is a finite sum, this is some number. What is this number? Tell me, what is this number? You see, the way we have constructed, rank of OK is this. So rank of O n minus 1 must be equal to m0 dot 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 up to m n minus 1. And what is that? What we have assumed observability. So this is the full observability matrix and its rank is n. So this is equal to n in fact. Yeah. So this sum is in fact equal to n, the state space dimension. Okay. All right. So this is what I wanted to get through, that if you look closely at these numbers also have some expressions. They can be understood in terms of a state space representation, and in terms of the state space representation, it turns out that first we have this fantastic property that rank of OK is given by this number, where these numbers are defined as before. Where did I define? Yeah, here. And then we find out that dk, okay, first expression, dk is this, rho k is this, and that implies rho infinity is this and m infinity is 0, and this is what we have. With these two things in fact, these things in fact, we will be able to derive this persistency of excitation idea, as we will do in the next couple of lectures. Okay. I think I am almost out of time here, right. So using these facts, we will discover, or we will rather reinvent how the idea of persistency of excitation comes in, and the fact that persistency of excitation will imply that this finite time series data that we have, from which we construct this finite Hankel matrix, that finite Hankel matrix's column span will be exactly equal to the behavior restricted to that size. Okay. This and many more is what we are going to see in the next few lectures. Till then, take care of yourselves.